So today we will do a new topic, shifting actually from all the things we have done thus far, which are discussing algorithms and giving upper bounds of running times for algorithms. Now what I would like to discuss is a very important topic of lower bounds. How do you prove that no algorithm can run in a particular time? So let's just a second. There. Excuse me. Sorry, it seems to be still a bit unfocused. All right. So what is the topic? This is actually a very important and challenging topic in the analysis of algorithms. Lower bounds. So how to prove that there is no algorithm that can run in, in some time t event. So for example, for sorting and numbers, there are many O of nlog n time algorithms. And you might ask, why nlog n? So we get nlog n from merge sort, from heap sort, from randomized quicksort, maybe by actually inserting all the numbers in a red-black tree and then doing deletions. That also gives nlog n. And so there are multiple ways in which one can sort n numbers and sort of arrive at this. Oh, I'm sorry. Arrive at the nlog n runtime. And so you might wonder, well, can you do anything better than nlog n? And surprisingly, the answer is no. But one has to sort of be very careful about this. I'm going to make a statement first, and then I will start explaining what it means. So we can prove that there is no, so here's an important phrase, comparison-based sorting algorithm. Comparison-based sorting algorithm that runs in fewer than, then essentially n log base 2n steps. Up to some, okay, so maybe, minus some sort of theta of n term. But the point is, you can actually prove that n log n is the right bound for comparison-based sorting algorithms. So what this means is, what is a comparison-based sorting algorithm? So a comparison-based sorter means the algorithm can only compare the values in a single operation. Compare, let's say, two values. in a single operation. Now you might think, okay, so what else can one do? But suppose, for example, there are situations where one can do more than comparisons. So for example, suppose the input consisted of k-digit numbers. An algorithm could inspect the individual digits. Right? And this would not be comparison based. This is not comparison based. So is this clear? Any questions about this? What it means to be a comparison-based algorithm? So all the algorithms that you've typically seen, merge sort, quick sort, heap sort, or anything that involves like binary trees or any data structure of that form is a comparison-based algorithm. It's only using comparisons to compare numbers. So someone points out, yes, so like radix sort, for example, is not a comparison-based sorter, because it actually uses the individual digits of each number. In a comparison-based sorter, one is only allowed to compare the values.
And what are other options? Like, you should compare anyways, compare something anyway, right? Or is there another way that I cannot
No,
think
for
of?
example, suppose you knew that all the numbers were integers from 1 to n. And there are n of them. Suppose, okay, so for example, another example of what you can do is something called counting sort. So in counting sort, the input only consists of, I'll say natural numbers up to n. Where n is actually, let's say the input consists only of at most n natural numbers up to n, right? In which case what you can do is you can actually go and count how many times each element appears and use that to actually sort. So in this case, you can sort faster. You can actually sort in n times. So for example, if your input consisted only of numbers, I'm just giving a simple example. Here's 7, 3, 2, 1, 1, 7. 10, 9. Suppose this was your input. You knew that all the numbers were from 1 to 10. What you can do is you can actually say, count how many times 7 appears. So 7 appears twice, 3 appears once, 2 appears once. And using those counts, you can actually go back and read. So just to give you an example of how this would work, suppose you knew what you do is the way that you sort is you create an array of size 10. Okay, so here's an array of size 10. You look at the first element, you say, oh, there's a 7 there. So I look at the 7th element and I increment. I say, oh, there's a 3. So suppose the numbers were going from 0. I could go to the third cell and say, oh, I'm going to put a 1 there. 2 appears, I'm going to put a 1 there. 1 appears, I put a 1 there. 1 appears again, I increment this to 2. Then 7 appears again, I increment this to 2. 10 appears, I put a 1. 9 appears, I put a 1. So I can do this in linear time. Then I can actually go back and read out the sorted order because I know that 1 appeared 2 times, 2 appeared once, 3 appeared once, nothing else appeared, then 7 appeared twice, so on and so forth. So I can essentially index how many times a particular number appears and use that to actually get the sorted order. Does that answer your question? Right, so that's an example.
Yes, thank you.
So somebody asked, does this mean that sorting strings of max length n can be done in n? No. So actually, when you're doing radix sort, it's actually n times k, where k is the number of digits. So if you did something like radix sort on strings naively, you'll actually get n squared. So you actually have to do something more careful. But again, strings are also a good example where you can actually look, you can inspect the individual characters of the string. But indeed, what you can do with strings, just to give an example, is that you know that strings, they're coming from this alphabet. And so often what you can do is you can then index by the first letter, break it up into a bunch of groups, and then try to sort them, faster than doing something like merge sort or quick sort. So this is, this is a very useful discussion that we're having, because to prove the nlog n bound, you have to kind of understand the notion of a comparison-based sorter. And that concept is fundamental to being able to prove such a bound. Okay, so any other questions about this? Okay. I want to take my time and do this somewhat slowly, because even though in the end the proof is short, it involves many deep ideas which have become very influential in the mathematics of algorithms. Okay, so let's try to think about what is the output of algorithm. So yeah, I just quickly looked at the chat. Yes, what we're saying is that for every algorithm, there exists some input that causes to run it in n log n time. So maybe this is worth writing. So what do we want to prove? The theorem is, okay, so I'm going to state this in multiple ways. Every comparison-based sorter runs in omega n log n time. Another way of saying this is that if a sorting algorithm only uses comparisons to determine the final output, there exists some input where it runs in at least Cn log n steps. So C is some fixed constant. So basically what it says is there exists a constant C. It's important that this constant is decided beforehand. There is actually some absolute constant. That this absolute constant turns out to be, I think, it's almost like, you can essentially treat it to be like 0.9. There's an absolute constant, so that if any sorting algorithm only uses comparisons, it runs in C n log n time. The constant does not depend on the algorithm. The constant is independent. That's what this lower bound means. This is important, right? So there is some absolute constant, so that if a sorting algorithm only uses comparisons to determine the final output, there is some input where it runs at least Cn log n steps. This input is called a hard instance for that algorithm. Note that the hard instance doesn't have to be hard for all algorithms. Each sorting algorithm may have a different hard instance. Some sorting algorithms may be able to sort a hard instance for another algorithm in linear time. This is not saying that, it's not saying that it always runs in n log n. It says there exists some input, because we're doing lower bound for worst case. This is the lower bound for worst case. Although indeed this theorem is robust, the proof actually also works for average case. It also says that actually you can actually construct, essentially it's kind of, say, I will formalize this, but essentially even on a random input, where random is suitably defined, you can actually show that even on random inputs, it's going to take at least n log n time. So there will actually be many inputs where the algorithm is going to take n log n time. So any questions about this? Okay. What will be important to formalize this theorem is to really ask, and this is what actually is very interesting about the study of lower bounds, that you have to ask very deep fundamental questions about what does it even mean for an algorithm to have the correct answer? What does it even mean to output something? So we can ask, so let's begin by first asking, what is the output of a sorting algorithm? What is the output of a sorting algorithm? And you might say, well, the output is just a sorted order. Of course. But this actually becomes a little harder to argue with. So let's say that suppose the input was a permutation pi of 1 to n, or any n numbers, it doesn't matter. The output is always the same. So here's the problem. Suppose I told the algorithm that the input is going to be a permutation from 1 to n. Well, then there's a linear time algorithm to do it, because it will just output the same permutation. It'll just output 1 to n. Okay, so let's be careful here. What I'm saying is, suppose I told you that the input was a permutation from 1 to n, and I say, you need to sort this permutation. We say, that's obvious. The output is just 1, 2, 3, 4, 5, 6, up to n. But that seems to be cheating. It's not capturing what the algorithm is actually doing. So what I'm going to argue is that the output of the sorting algorithm is not just a sorted order. It's also the permutation induced by the input. Okay, so let me make this precise. Let me say that a sorting algorithm, a correct sorting algorithm, should specify, a correct sorting algorithm should specify the following. So let's say that the input array is A. Right? So A, we can just think of as, and it's going to be convenient. I'm going to sort of apologize for this, but I am going to index my arrays from 1 to n as opposed to 0 to n minus 1. So it's going to be just somewhat convenient. So here's my input array. I'm just going to index from 1 to n. So the sorted order, which I'll call A sort, is something else, where we could think of all the initial indices have been moved somewhere. What you have over here is a permutation. So I could say a correct sorting algorithm should actually just specify this permutation. A correct sorting algorithm should actually output So not just it's outputting the sorted order, but you can think of it, it's also really telling you where each input index should move. And that's a permutation. So for example, I could say, let's define pi of I to be the index of the final position of A of I. And I could say a correct sorting algorithm should actually tell you what pi of I is. It should tell you where each input ends up. And if you think about it, every time you sort, every time you do an operation, a data move, you could keep track of this. You can keep track of this exactly in the, so every time there is an operation that's, so usually what does your sorting algorithm do? It does a swap. It moves something somewhere. Right? It moves something somewhere. And you could use that to keep track of where a particular element is. Does that make sense? Any questions about that? I'm happy to say this again, but please ask me questions if there's something that is unclear. I'm going to say a correct sorting algorithm should really tell you where each element finally ends up. And that's the permutation that is induced by the input. Indeed, if pi of I is equal to I, that means that the original array was already sorted. If pi of I is equal to n minus I, then it was in reverse sorted order. But in general, a correct sorting algorithm is essentially implicitly telling you how to move things.
In the example you gave, where you tell the algorithm that it is a permutation ahead of time,
right?
Wouldn't it still be able to just do this? Just inspect all of the indices of the permutation and tell you where they should go. It's not any harder to do this for that algorithm, right?
You're absolutely right. You're absolutely right. You're absolutely right. But on the other hand, now think about, suppose you have to generate this index by only making comparisons. You're only allowed to compare the elements. So you start with some input and you have to compare things and decide where they go. So you're not allowed to actually look at the actual number that's there because it's a comparison-based sorter. It's a comparison-based sorter.
Professor?
Yeah, yes.
Would a better way of saying what the correct sorting algorithm should specify would be like at each step of the operation, you have to show the permutation at that state. So that way there's no sort of like reverse engineering hack we could do.
No, so it's very hard to argue about what the internals are doing, right? I mean, actually, that is one of the things that... Okay, so let me answer that question in a bit. But yes, at some level, that is what we're going to argue, but I don't want to specify that because specifying the internals of an algorithm is really hard. But specifying what it should output is a lot easier.
Okay.
Okay, specifying the output is a lot easier. Okay, so someone, I believe, asked, excuse me. How do we remember the initial position of the elements for pi when we keep swapping? Okay, so let me actually let me suggest something over here. So let's just say, I mean, I'm not, okay, so this is to answer the question of how would an algorithm actually keep track of this position, right? That's really the question. And you can observe, and this is going back to the previous comment, that given any comparison-based sorting algorithm, let me show you how you can get this sorted, how you can get the permutation without extra running time overhead, just a constant running time overhead. Okay? So I'm going to sort of sketch this argument out. So let's just say that at any stage, and this is now going back to the previous comment, the algorithm makes comparisons and data moves. Right? That's basically what the algorithm does. For each data element, suppose we stored the index from the original input. So I'm doing a thought experiment here. What I'm saying is, so let's say this is your algorithm, and your algorithm has some data that's stored. Right? It's basically storing some data. Some of it is the original input, some of it is something else. I'm just going to maintain an auxiliary memory that says, oh, this element, this was the ith element, this was AI, that was AJ, this is I prime. So this is just maintaining the index of where it came from, so on and so forth. So suppose I maintain this index. Now, anytime the algorithm copies an element, I can just copy this index. If it swaps two elements, I can do the corresponding swap. Right? And this would keep track of where that element ended up. So I would basically end up with, I would essentially end up with the inverse permutation. And then you can actually just get the forward permutation again. But let me explain this, and then I can explain what you finally get. So pi I is this. We can also think of sigma I. So sigma I would be the opposite. So here sigma I is the original index in A of A sort of I. It's the original index. So for example, sigma 1 would be where it came from. Sigma 2 would be where that came from, so on and so forth. If you have sigma, then you can see that you can go back and construct pi in linear time. Because if you know that, let's say this was 5, then you know that tau of 5 is 1. This is just inverting the permutation. If you know this value is 2, then you know that pi of 2 is 2. So on and so forth. And observe that keeping track of sigma is really easy. So the auxiliary, so I will explain this again. So for each data copy or move, because what's happening is there's just data is being copied and a sign. That's the only thing that happens in your algorithm to actually determine the sorted order. We can keep track of the original index. Right? So if this cell, whatever was copied to here, well, then you would say, oh, I'm just copying I. And so eventually, in the output, we have the original index. Excuse me. We have the original index of each element, which is sigma. Does that, whoever asked that question, does that answer your question? Like, you can see that how you can get sigma, and once you get sigma, you should be able to get pi. But if that bothers you, then just assume that the output is going to be sigma. Okay, so any questions about what we have so far? So what does all of this discussion say? What this discussion does is to sort of say, whenever you have a correct sorting algorithm, you're kind of computing sigma as you go along, just by this process that I described here. So what I described here tells you that you can imagine that sigma is also being computed, because for every data copy or move, you can keep track of the original index without extra running time overhead, or rather with a constant factor running time overhead. We can keep track of this, and only constant factor overhead in the running time. Like, there's only a constant factor running overhead in the running time. Yeah, so someone asked, are we keeping track of the indices just to prove the correctness, or is it useful to implement? So this is not for implementation. To some extent, this is not even to prove correctness, but rather this is going to help us prove the lower bound. What you will see is that the fact that you can always keep track of sigma, and hence pi at the end, this shows that any correct sorting algorithm essentially computes sigma. Now, what is the benefit of this? What is the benefit of this is now let's look at consider a comparison-based sorting algorithm, a comparison-based algorithm that I will refer to as S, right? This is my sorting algorithm, S, script S. S must also output. Okay, so instead of pi, let's actually deal with sigma. Must also output sigma. Remember, sigma I is the original index. Is the original index of a sort of I. Okay. Okay, now suppose the input was just a permutation pi of 1 to n. So suppose that was just the input. And suppose S even knew that that was the input. S knows that the input is just a permutation from 1 to n. But S now has to output the corresponding sigma. S has to output the corresponding sigma. Okay, so let's kind of see what this is. So pi is essentially a permutation, right? And so if you think about what pi of I is, as we discussed before, okay, so maybe I should say this, sigma is going to be pi inverse. Formally speaking, what do I mean? I mean that if sigma I is j, what does that mean? It means that, so this is the input, pi, and this is sigma. So if sigma I is j, this means that the original index of whatever ends up here is j. But in the sorted order, if you look at what A sort is, what goes here in A sort, in the ith position? What goes in that position in A sort? So A is just, so the input A is just a permutation, pi of 1 to n. If you sort the permutation, what goes in the ith position? It's just I. It's just I. Which means sigma I is j, which means that I was originally in the jth position. So sigma I is j is equivalent to saying pi of j is I. And that's what this means. So the output you can think of is just the inverse permutation. The output is just the inverse permutation, right? We said that you must output the original index of everything. The original index, basically, at the ith index of the sorted version, you just have I. And if sigma of I is j, it means that I was in the jth position in the beginning, which means that pi of j, which is an array, permutation is an array, is I. So sigma is equal to pi inverse. Moreover, a simple claim that you can verify is that distinct permutations have distinct inverses. Okay, why am I saying this? For every distinct input permutation, the output of this algorithm S is distinct. Okay, it's just saying that if you gave it different permutations, it's going to give you a different answer. All right, so far so good? Okay. Okay, now we will do yet another operation. Okay, so we have this so far. Let us construct the comparison tree induced by the algorithm S. So what this means is we ignore all the data moves and only track the comparisons. Okay, so what do I mean is, let's look at the running of the algorithm. Let's look at the running of S. Okay, so let's look at the running of S. What it does in any particular node is at the very beginning, it's going to make a comparison. So maybe it'll compare AI less than AJ. It's going to ask, is AI less than AJ? And so the answer would be yes or no. This is the comparison. Now, based on this comparison, it'll make another comparison. Maybe it'll say, is AI less than AJ plus 1 or something, whatever. And it's going to be yes or no. And maybe here what it does is it looks at AI plus 1 less than AK, and it will be, again, yes or no. Note that I don't care what data moves are being made. I'm just tracking what comparison is made by the algorithm. So every time, if the comparison is the same, the output will be the same. This is really important. The point of a comparison-based sorter is, if comparisons are the same, the output is the same. So what the algorithm S does is it does a series of comparisons, and finally it ends up at an output. So what it'll say is that the output is some permutation sigma. Because we said that to give the output, we want it to output sigma. So it's going to do some series of comparisons and end up at an output. Is this clear? Any questions? Any questions about this? Okay. So this process continued. There may be two different ways it can give the same output. That's completely fine. These can be the same. Maybe it does some sequence of comparisons, decides that the output is something, does some other sequence, although it's unlikely that that would happen. But I'm just saying that hypothetically, the algorithm can do anything. The only thing is it's correct. Okay, now here is so every leaf is an output. And we said that every permutation, every distinct permutation pi leads to a distinct output, sigma. Okay, now here's the question. How many leaves in the comparison tree? How many leaves are there in the comparison tree? At least, I should say at least. At least how many leaves? Give me a lower bound on the number of leaves. Yes, anyone? Right? So the answer has been posted in the chat, but does everybody see? Someone want to comment? How many leaves? Well, you have at least one leaf for every permutation, right? So at least one leaf for every permutation. So hence, the number of leaves is at least n factorial. Okay, now observe the following. Consider a path. And suppose the length of this path, suppose the length of the path is L. Then the running time on the input is at least L, because you have to make all the comparisons. Maybe there's also even more work in moving data around. Maybe there's some work that is done in deciding how to go from one comparison to the next. But in general, or not in general, but for every path, the length of the path is a lower bound on the time. The time is at least the length of the path. Okay, this is very important. Right? So for any leaf, the distance to the root is a lower bound on the time, on the computation time. Computation time, for that input. And so the height of the tree is at least log base 2n factorial. Why? It's the log base 2 of the number of leaves. Okay, so I'm just now going to state something here as a claim, which you can, easily you can prove this claim by induction. The claim is, in a binary tree with k leaves, the height or max depth or whatever you want to call it, it's all the same, is at least log base 2 of k. Right? So in any binary tree with k leaves, the height is at least a log. And so the height of the tree is at least log base 2 of n factorial. What this means is that the worst case running time, is definitely at least the height of the tree, height of the comparison tree, which is at least log base 2 of n factorial. How much is that? How much is the log base 2 of n factorial? Anyone wish to hazard a guess? Can you give me a quick and dirty bound? Just give me a lower bound. N squared? O of n squared? No, it's actually going to be much larger than the log base 2 of n factorial. Upper bound, yes, but I want a lower bound, right? Because we need to lower bound this quantity.
Log base 2 of n.
It is definitely at least log base 2 of n. Sure. Okay, now give me a better one. So let's write this out, right? So log base 2 of n factorial is what? It's the summation I going from 1 to n of log base 2 of n. Using this, can you do better than log base 2 of n as a lower bound?
Maybe log base 2, No, sorry. I was going to say log base 2 n to the n, but that might be upper bound actually.
Log base 2 of n to the power. No, because you're multiplying things, right?
Mm-hmm.
Okay, so someone said n log n by 2. Why? Okay, someone said there are n terms. Of course, not all of them are log n. Like some of the terms are really small. I want a lower bound, right? I want a lower bound, not an upper bound, because I have to give a lower bound to the worst case running time. But you're almost there. Instead of n terms, maybe you want to try to look at what are the largest terms in this. You want to take the log out of the sum. Well, I mean, it's technically, log is a concave function. You could try to do something with that, but it's it's much easier. You can get a constant factor lower bound with far less work. What if you just did this? This is at least I going from n over 2 to n of log base 2. Oh, I'm sorry, this should be I, not n. I'm sorry, I, log base 2 of I. I'm sorry, right? Log base 2 of I. My apologies. Right? It's summation. It's like, log n plus log n minus 1 plus log n minus 2 plus log n minus 3, so on and so forth. I'm really sorry. It's not log base 2 of n, but log base 2 of I. Okay, is this clear? Now what? Can someone give me a lower bound for this now? Just give me a quick and dirty bound, right? So you know that each of these i's is at least n over 2. Yes? Surely this is at least I going from n over 2 to n of log base 2 of n over 2. And that last one is now easy to deal with. That's just equal to n over 2 log base 2 of n minus 1. Right? And this gives me my bound of n log n by 2 minus n over 2. But of course, this is a lower order term with respect to that. And so this is omega n log n. I will show you a better bound, but this tells you the worst case running time of the comparison based sorter is omega n log n. N log n comes up precisely because it's the log of n factorial. That is in some sense the deep insight. This is a very deep and important proof in the analysis of algorithms. It's an important theorem and important proof. There are multiple ways of interpreting this. But the point is the worst case running time is at least n log n. And it's n log n because n log n is the log of n factorial. That's why n log n comes up in sorting. And I showed you how you can prove the n log n using a quick and dirty argument. Any questions? Any questions? Just as a comment, I think this is sort of an important point, a side comment, is there is something known as Stirling's approximation. Something called Stirling's approximation. So sorry, let me just silence some things here. All right. Stirling's approximation says that n factorial is asymptotically square root 2 pi n divided e to the power n. This is one of the most beautiful things in mathematics, that looking at factorials, right? Factorials is just ordering, like how do you order n things? It's actually related to pi and e, two of the most fundamental constants in mathematics, right? I mean, how crazy is that? Factorials, which seemingly have nothing to do with anything related to circles or with exponentials. Well, okay, it's an exponential, but with e, the constant e. But actually, n factorial is asymptotically square root 2 pi n over e to the power n. So if you use Stirling's approximation, then what you get is that the log base 2 of n factorial, if you take the log base 2 of n of this, what you get is it's basically n log base 2 of n, minus essentially some kind of n term, minus something that is really small, right? Because you'll get n log base 2 of e, plus log base 2 of square root 2 pi n, but all of these things are really small. So what you get is n log base 2 of n minus theta of n. So essentially, the constant is tight. It's just 1. Whereas what we got here was a half. We showed that log base 2 of n factorial is at least n log n divided by 2. It's actually pretty much closer to n log n, just directly with no constant loss here. Okay, so Stirling's approximation can be used to actually give you an accurate approximation here. But the point of this discussion was that the worst case running time of any comparison-based sorting algorithm, I repeat, any comparison-based sorting algorithm is at least n log n. And indeed, if you plug this in, you get that the constant is also, it's n log n minus some theta of n term. Very fundamental theorem. Please ask me questions about this if anything is not clear. So I'll just poll and ask you, would you like me to go over the proof again? Sort of at A is yes, B is no. A is please go over the proof again. B is no, I understand, you can continue. Okay, I think that there are enough people who would like me to go over the proof again. So let me do that. And let me go back and start from the beginning. Not the beginning, but almost the beginning. Okay, so we wanted to prove that every comparison-based sorter runs in omega n log n time. That there exists a constant C such that if a sorting algorithm only uses comparisons to determine the final output, there exists some input where it runs in at least Cn log n steps. Indeed, this C can be made arbitrarily close to 1. That's the point of Stirling's approximation, but getting a half is really easy. Okay, or easy, really easy, but whatever. There is a simpler calculation. Now, to formalize this, let us first try to understand what is the output of a sorting algorithm. Well, you could say it's just the sorted order, but I want to say no, the sorting algorithm should also figure out the permutation induced by the input. Okay, let me make that precise. So look at an input array A. It is sorted, which means that all the elements are eventually moved to some position. Sigma of I would be the original index in A of A sort of I. So if you look at A sort of I, so look at the sorted version, look at the ith element, and you say, where did the ith element come from? J. That you could think of as actually, I would like that to be the output. Now, what we argued was that any correct sorting algorithm should be able to get sigma as well, with a constant factor overhead and runtime. In some sense, sigma you would imagine, we discussed how you can actually tweak the algorithm or just keep track of what the algorithm is doing and extract sigma out without more than a constant factor overhead in the runtime. So what this means is, if we consider a comparison-based sorting algorithm, script S, we can imagine that S should also output sigma, the permutation, where sigma of I is the original index of A sort of I. Now, if the input was itself a permutation, then sigma is really just the inverse of that permutation. Which means that you want a comparison-based algorithm that inverts permutations, that given a permutation outputs the inverse. That's really what it boils down to. But the algorithm can only make comparisons. It cannot do anything else, right? Because it cannot look at the numbers. It can only make comparisons. How is that manifested? We will look at something called the comparison tree induced by script S, which means we ignore all the data moves. We only track the comparisons made. What we get is called a comparison tree. So if you look at the running of S, you can say the first thing it does is it makes some comparison. Maybe it compares A1 and A2. And depending on the comparison, it will decide to make another comparison. So it does some data movements here, but we will ignore the data movements and say, okay, finally it makes a comparison, then yes or no. Okay, then it goes yes, it goes no. And then it makes a comparison, so on and so forth. Note that if the comparisons are all the same, then the movement down the tree will be the same. And in the end, it has to provide an output. The leaf is an output. It could be the case that different leaves will actually lead to different leaves could even lead to the same output, although here one can see that it would not be possible with this example I drew. But in general, there is nothing that precludes that. On the other hand, every distinct permutation leads to a distinct output and hence a distinct leaf. If you change the permutation, so remember, we are going to only input a permutation from 1 to n. And if the permutation we input is different, then we get a different output. So the number of leaves in this tree has to be at least the number of permutations, which is n factorial. Now for any leaf, if you look at the path from the root to that leaf, the length of the path is a lower bound on the running time, because the running time has to, the algorithm has to make those comparisons at least. It has to make those comparisons because the algorithm, as we said, is going to make that comparison, which is one operation. Maybe it does even more because it has to move data. We're ignoring that. So the distance to the root, that is from the leaf to the root, is a lower bound on the computation time or the running time for that input. So the height of the tree is at least the log of n factorial. It's the log of the number of leaves. And this is just a claim that in a binary tree with k leaves, the height is at least the log of the number of leaves. So the worst case running time is log of n factorial, log base 2 of n factorial, and we prove that log base 2 of n factorial is at least n log n, is omega n log n. Indeed, by Stirling's approximation, it's very close to n log n. Very close to n log n. And so this sort of ends this discussion on sorting and the comparison-based lower bound for sorting. N log n appears because it is the log of n factorial. If you want a one-sentence summary, the running time of sorting is n log n because that is the log of the number of permutations. So this is a good time to pause. We'll pause for a few minutes. And then when we come back, I want to discuss a little bit more about this sorting lower bound and maybe something called an adversarial argument. I'll take questions in the meantime, but we can take a break for a few minutes.
Hey, Professor, I had
Yes.
one question.
Yes.
I just wanted to know, in that tree that you were showing us, are all the leaves the same height, or could some leaves be like higher than others because there's not as many comparisons needed? Like, what if it's already sorted? Then
Good question. Good question, right? So some of the leaves might be higher up and some might be lower down.
Okay.
That is very much true, but we are looking at the height of the tree, which you can think of as like the max. The point is, there has to be at least some leaf that is far down. All the leaves cannot be high up. Okay, that's what this claim says. If you have k leaves, somebody has to be at least a depth log k. Right? You kind of think of it as, because if the height is d or h, then there can only be 2 to the h leaves.
Right.
Okay. I mean, essentially, I just sort of verbally gave you the proof, right? If the height was less than log k, then there can be at most 2 to the power of the height leaves.
Okay. Got it.
Right? So if you have k leaves, at least one of them has to be at distance log k from the root.
That makes sense. Okay, so it doesn't have to be like a complete binary tree.
Not at all. Not at all. It actually will not be. Indeed, if you think about it, making it complete would be the best for the algorithm. Because then if it's actually far from complete, then more, some of the leaves might be much further than n log n. Right? This is tight when it's complete. When it's complete, that's basically an equality. But otherwise, it's actually a lower bound.
Okay. Got it. Thank you.
Does that answer your question?
Yes.
Yeah. Anybody here who has done information theory? Maybe some of the people who are electrical engineers may have studied information theory. Anyone? Yeah, raise your hand if you have. Okay, so some of you have studied information theory. There's actually a connection of this to entropy as well. So what it basically says is each comparison gives you one bit of information. And because you're trying to discover a permutation, you actually have to get log of the number of log of n factorial, which is n log n. You need a correct algorithm has to get or has to extract n log n bits of information. Each comparison only gives it one bit. So that's another way of, you can actually rephrase this entire proof in terms of information theory. And hence this is also sometimes referred to as the information theoretic lower bound, because it says that each comparison only gives it one bit. And so as it goes down the tree, it's gathering bits, and it needs to gather n log n bits to make a correct decision. Okay, we'll wait for maybe another minute before we begin. All right, so the worst case running time of a comparison-based sorting algorithm is omega n log n. Amen. many other lower bounds can be proved by doing what are called sorting reductions. Now, I don't want to go deep into what reductions are. I will leave that for the next lecture. But instead, what is a sorting reduction? It says that suppose we have an algorithmic problem that I'll call bold A. And we wish to prove a lower bound, a runtime lower bound for running time. Now that we've done all the effort for sorting, an approach is to say, if A could be solved in less than t operations, then we can sort in, say, less than nlog based operations. Suppose you prove this. So if A could be solved in less than t operations, then we can sort in less than n log n over 2, or any constant. You can put a larger constant there. The constant, the constant is unimportant, but you have to put some constant there, which is less than the constant obtained over there. So let's just say n log n over 2, just to be concrete. Suppose you prove this. That implies A cannot be solved in t operations. So this is what is called a sorting reduction. It says that the way that suppose you have some other algorithmic problem and you want to prove a lower bound, you argue that if you could solve A very efficiently, then you can sort faster. And you know that we cannot sort in n log n operations. So I should say comparison sort, comparison based. So therefore that implies that A cannot be solved in t operations. Let me give you, and this is commonly used for proving data structure lower bounds. So for example, here's a nice and compelling example that says in a binary heap, extract max requires, I'll say, at least log base 2 and over 2 operations. Okay, so this is actually a theorem. And so what is the proof? Well, suppose extract max could be implemented with less than log base 2 and over 2 comparisons. Then, to sort an array A, we basically build a heap, build a max heap on A, and then call extract max n times. So the first step, this is O of n. The second step is going to use less than n log base 2 and over 2 comparisons. So we can sort using essentially at most n log base 2n over 2 plus O of n comparisons, and that's a contradiction. Completing our proof. Does that make sense? So you cannot extract max in log base unless, and essentially, you need omega log n operations to extract the maximum, because if you could beat that, then you could sort faster. Does that make sense? Any questions about that? Right?
Doesn't building the max, why does building the max heap only take linear time?
So there's actually an algorithm that builds a heap in linear time from an array. Like you don't, instead of inserting n elements, there's a much more clever way of doing it where you can, where you essentially call the heapify operation in a particular order. It's a clever algorithm. You can check it out. Like you can actually build the max heap in linear time. It's faster than inserting n times.
Okay.
You would think it's n log n because you insert n times into a heap. But actually, there is an algorithm. If you just look at the build heap algorithm, it runs in linear time because it basically calls the heapify operation sort of in reverse order. Okay, any questions about this argument? So I wanted to do this to demonstrate the power of the sorting lower bound, because now we can argue that binary heaps are essentially optimal. One can prove, especially regarding data structures, one can prove, for example, inserting into a binary search tree requires omega log n comparisons. And again, essentially you can do this and then do a tree walk. You can follow the same argument as before. So sorting reductions are quite powerful. But moreover, one can look at the comparison tree argument or the proof strategy. And if you follow that, you can prove things like binary search in a sorted array requires omega n log n comparisons. Which, it's not, you might think, okay, of course, or not even, I shouldn't say binary search, sorry. I meant searching in a sorted array requires omega n log n comparison. You might think, of course, binary search takes n log n, and you can kind of see that splitting in the middle is the right thing. But how do you know that ternary search is not? So what if you do ternary search? Or maybe there's some clever algorithm decides to compare many different positions, sort these positions, then search amongst them, maybe is able to reduce the search space even more, and then does something strange over there. You never know. Maybe there's an algorithm that could do something much more clever than binary search and beat log n. But no, the comparison tree argument, if you basically do the argument that we did for sorting, you can prove that log n comparisons are actually necessary. One can even do something. One has to, in this case, it requires like tracking the constants carefully with Stirling's approximation. But essentially, you can say merging two sorted arrays. Merging two sorted arrays requires at least 2n-1 comparisons. Two sorted arrays of length n. So, of course, in this case, we're actually tracking the constant, not just because we know that we can merge two sorted arrays in linear time. But essentially, you can even bound the number of comparisons up to a constant. You can say it actually takes 2n comparisons, which is what our algorithm takes. Because you might say, no, could you do it maybe in 3n/2 comparisons? Can you beat that bound? And so it is natural to ask that question. And again, the same style of argument. So what is the style of argument? The argument, let me draw the comparison tree again. You kind of build a comparison tree. You track the comparisons, and then you argue that how many leaves are there, and then you bound the height of the tree by log of the number of leaves. Indeed, this is almost kind of telling you where log n for binary search is coming from. Where you get the 2n-1 comparisons, that requires, it basically comes from it requires Stirling approximation on a different quantity. But again, what you can do is you can prove a bound of that form. So this is a comparison tree argument. And I just, sort of wanted to show you the many different theorems that you can prove when you have, using these arguments. And so just to show you, sorry, where is the heap argument that I had over here? Okay. Sorry, I lost the page, but anyway, so inserting into a binary search tree requires omega log n comparisons. Extract max from a binary heap requires log n comparisons. Binary search requires, or not binary search, searching in a sorted array requires log n comparisons. Merging sorted arrays requires exactly 2n-1 comparisons. And all of these fundamentally go through the comparison tree argument. Any questions about this?
For search, is it okay just to say like you're trying to discover something that could have at least you're trying to discover something that has n possibilities. So there's log n bits of information and each comparison gives you 1 bit?
Exactly. I mean, it's the same thing. Yeah, precisely.
Is that a proof?
I mean, essentially, it's a proof if you know information theory. Otherwise, you have to sort of state what the comparison tree is.
Okay, sure.
Right? Because the moment you say that, oh, it's 1 bit of information, then you kind of have to formalize what information is and things like that. And in some sense, the writing out the comparison tree is that formalization. I mean, if you just describe it as a comparison tree, then that's
yeah, that makes sense.
That's pretty much it. Yeah.
Would log n be considered the lower bound if, let's say you got lucky that binary search found the target in less than log n comparisons?
Mm-hmm.
Well, wouldn't that make log n actually an upper bound because that's the worst case amount?
Okay, so the point is, what does omega log n mean? It means omega log n in the worst case. It means that no matter how you do binary search, there's always some instance that's going to lead to log n. Now, maybe I should have stated this precisely in the worst case. Right? This is all in the worst case. There could be instances where you beat this bound, but the same algorithm cannot beat it all the time. Does that make sense?
Okay, worst case definitely helped.
Worst case. Yes, so someone asked about the log n for searching in a sorted array. Could you repeat it? Maybe if you can ask me exactly what was unclear. So I'm just saying that there is a theorem that says searching in a sorted array requires log n comparisons in the worst case.
And did you prove that?
I didn't prove it, no.
Oh, okay, that's the thing that was
There was just a
confusing me.
discussion. There was a discussion that hinted at the proof because it says that the number of possible outcomes is n.
Yeah. I got the information
So you
theory
kind of
thing.
have to formalize that because you're only making comparisons, and if you look at the comparison tree, essentially each decision leads to a different leaf and things like that.
Thank you.
Now there is something that that's kind of curious here. Indeed, I don't have time to do this in 5 minutes, but I will state this nonetheless. So what about searching in an arbitrary array? How long does that take? Anyone? So you just have an array and you need to find something.
Oh, man.
It takes n, right? But the information theoretic argument doesn't seem to work there. I mean, the comparison tree, you'd say, well, okay, there are n different leaves, and so the depth is log n, and you get back at log n. The answer should be n. But the naive comparison tree approach only gives omega log n lower bound, gives an omega log n lower bound. Because it would say, well, okay, there are n possible outcomes. And so what you get is really the log of that. And so you might ask, how do you deal with a situation like this? How do you prove? It seems kind of obvious that searching in an arbitrary array should take n comparisons. To prove this, there's a different style of argument called the adversarial argument. So the adversarial argument is a way of proving this. And using the adversarial argument, you can even prove something like finding the minimum in an array, in an arbitrary array, takes n minus 1 comparisons. I haven't told you what the adversarial argument is, but the point is, information, or rather these sort of comparison tree lower bounds, which are also called information theoretic lower bounds, the way as I described it is not the be all end all of things. Indeed, there are many problems where you kind of know that the answer cannot be the log of the number of outcomes. In general, the comparison tree argument can only give you something that is the log of the number of outcomes. And so there are n factorial outcomes, you get n log n. There are n outcomes for binary search, or n outcomes for searching, so it's log n. In merging, essentially, you can argue that the number of possible inputs is 2 to the 2n, and so you get 2n. But searching in an arbitrary array, finding the minimum of an arbitrary array, the answers you think are n, where n is really the number of outcomes. So how do you get the number of outcomes, not the log of the number of outcomes? There's a different style of argument called the adversarial argument. And so the way that the adversarial argument works is, okay, so at this point, I think I'm not going to draw much, just a few minutes. Essentially, you think of an adversary who's constructing the input as the algorithm proceeds. And the adversary is trying to fool the algorithm. So you almost set this up as a game between an algorithm and an adversary, and then you kind of analyze how that game proceeds, and then you can prove bounds of this form. So I might, maybe do some of that in the next lecture or talk about this in some of the subsequent lectures, but this is a good point to end. And so again, I want to end with the fundamental theorem that I said, I think if there's sort of the one sentence message for today, it is that the worst case running time of a comparison based sorting algorithm is omega n log n, because that is the log of the number of permutations. So with that, I'll end and take any questions that you have.